We are discussing atomic radii. If you remember, basically I was telling you, the issue with measuring atomic radii is, we are facing difficulties because of Heisenberg's uncertainty principle. Because if you look into the atomic radii definition, it's from the nucleus to the outermost shell. It's basically from the nucleus to the outermost shell. And shell itself is electron. I was asking you to view that shell is no different from electron. Electron itself is shell, and both are synonymous. So in that case, someone asking me to take an atom in my hand and cut it off and take a scale and measure would be a difficult proposition, for the simple reason it is impossible to determine what position of an electron because of the Heisenberg's uncertainty principle, which he was explaining. It's impossible to determine what the position of the electron, he says. And the other thing is, first of all, you cannot view electron to be having a regular boundary like a ball. It will be having an irregular boundary. And also, the issue is also, since electron is viewed as a wave, and the wave will be having a diffusing property, you must understand this. In all these three conditions, it's absolutely not possible to determine exactly, without error, the finding atomic radius would be a difficult thing. So hence what we have done yesterday in the previous classes is we have gone in for an operational definitions. But the issue is, when you get into operational definitions, then the issue becomes an error will be creeping into it. If you wanted no error, then you have to stick to the idealistic definition, and ideal things don't exist. So hence I was proposing 4 operational definitions for atomic radii. For one, we are actually having 4 operational definitions. So there must be some basis. So you must understand that the isolation of atom was difficult. Then what we have done is we have taken 2 atoms. When you have taken 2 atoms, then we have to ensure that the atoms are very close to each other. And the situation where atoms are very close to each other is basically when they are actually in bonding, participating in bonding. And in chemistry, we have no one bonding. You have covalent bonding, you have ionic bonding, you have metallic bonding, and you have no bonding. Sometimes people don't participate in bonding, like inert gases. So since the basis for your shift from idealistic definition to an operational definition, you're shifting from idealistic to operational, then the basis forms bonding, nature of bonding, and the nature of bonding in chemistry is not 1, and you have 4, and thereby I propose 4 operational definitions to you. If you recollect, I was basically telling about this. Atomic radii, we are discussing about this, atomic radii, and I was proposing 4 operational definitions. The first one was covalent radii, the other one was van der Waals radii, the other is metallic radius, and the fourth one is ionic radii. And since we have encountered some issues with atomic radii, and then we were proposing 4 operational definitions for you, and the basis for this, this classification is basically nature of bonding. Nature of what? Bonding, you must understand, nature of bonding. So if I can give some why 4 classifications are required, I draw the attention of everyone. If you actually see, you are supposed to isolate an atom. Isolation of atom is difficult. You must understand, it's a difficult thing. You can't isolate an atom and then cut it off for finding atomic radii. You must understand this. So isolation of one atom was difficult. So I was basically taking 2 atoms, and when I take 2 atoms, error creeps in. You must understand this. Error creeps in. It creeps in. You must understand, error has crept in. Error has crept into it. Now the only thing is, the legitimate thing is, you have to reduce the error or minimize the error or legitimize the error. You must understand this. So you can only minimize the error once these 2 are very close. So we have to ensure that these 2 atoms are close to one another. You must understand, your isolation of one atom was difficult for you. It's basically difficult. So we have chosen 2 atoms. You must understand. And we have chosen 2 atoms. Error has crept into your life, right? Error has crept into your life. Then what happens is, you have to ensure that the atoms are very close to one another. And the atoms will be close to one another only the situation is when they participate in bonding. You must understand. And when you say where they are close to one another only when they bond with each other, and the bondings are 4 types, you must understand this. One is the covalent bond, the other is van der Waals, the other is metallic, and the other is ionic, because you have ionic bonding, you have covalent bonding, you have metallic bonding, and some people don't participate in bonding, and how do you handle them, right? These are the issues that crop up. Actually, the idealistic definition has poses us some issues, hence we are forced to give alternate 4 operational definitions, what I call them. Operational definitions in the sense we are able to what? Measure it. If you hang on to the idealistic definition of atomic radii, you will not be doing anything. You must understand this, because isolation of one atom is difficult. So you are supposed to take 2 atoms, and error has crept into your life. You have to live with error. The only thing left for you is minimize the error. And in the process of minimizing the error, the only option left for you is the atoms must be close to one another. And when the atoms are close to one another, such a situation in chemistry is only when we are bonding, right? So if you remember, if I recollect, now covalent radii versus van der Waals radii, yesterday I was telling you, if I draw the pictorial representation of what we have done very quickly, a recap of what we have done, such that I can move forward. And here is the covalent radii. You must understand this is the covalent radii of the hydrogen molecule. You have 2 nuclei, and this I'm speaking of hydrogen molecule, right? The internuclear distance between these 2 and make it half. This is covalent radius. That's covalent radius. And I was telling a question related to this. Mind you that this entire distance what we are speaking is nothing but the bond length. So I can simply say bond length is equal to 2 into covalent radius, or covalent radius is bond length by 2. You must understand, that's a question. The exam might give you a bond length or covalent radius. Accordingly, you have to find it out. So basically, that is how the covalent radius is. This is only applicable for atoms which participate in what? Covalent bonding. Now coming to the van der Waals radius, first of all, understand that, this van der Waals radius is basically proposed for people who don't participate in bonding. And in the entire periodic table, there are inert gases which are much fit into for van der Waals radius. You must understand this, right? Because inert gases, they don't participate in bonding as it is unless under drastic conditions. You must understand this. I won't say a sweeping statement that inert gases won't participate in bonding, but yes, they do it under drastic conditions, right? So you must understand that. So basically, van der Waals radius is only proposed for atoms which do not participate in bonding, right? For theoretical importance, what we do is we can actually apply the van der Waals radius even for hydrogen atom, to check out how much bigger is the van der Waals radius compared to what? Covalent radii, right? But otherwise, it's prudent or wise on your part to stick to what? Covalent radius in case of atoms that participate in covalent bonding. There is no business of, applying van der Waals radius to people who participate in what? Covalent bonding. It's absolutely for theoretical importance to know how much bigger is covalent radius compared to what? How much bigger is van der Waals radius compared to what? Covalent radius. That's what is a theoretical, thing, but otherwise you have no business to actually find out what? Van der Waals radius for people who participate in covalent bonding, like what? Hydrogen, chlorine, fluorine, or whatever. You must understand this, right? So if I can apply this for hydrogen molecule just to check out how much big is van der Waals radius, of course it will be bigger for the simple reason. You look into this diagram, I'm just comparing this. This is one hydrogen molecule. This is one hydrogen molecule with 2 nuclei. This is hydrogen molecule, right? And this is another hydrogen molecule, mind you this. This is a same hydrogen molecule, another hydrogen molecule, right? You must understand this. And then he is telling the internuclear distance between these 2 adjacent atoms, of 2 adjacent molecules. This is a molecule, that's a molecule, you must understand. So you have 2 adjacent molecules in which you have 2 adjacent atoms, and he's telling that the condition is you must be having van der Waals forces between them. You cannot allow these 2 molecules to enjoy the freedom. You must understand the molecules must be close to one another. They must be close to one another and ensure that there exists a van der Waals force between them. Then only you're supposed to what? Measure van der Waals radius. You must understand that, right? So they are very close and you have a van der Waals force between them, right? Once the van der Waals forces are existing under, right? And then you take the internuclear distance between these 2 and make it half. This is van der Waals radius, and if you compare this is what? Covalent radius, you must understand, right? So I'm just comparing hydrogen with what? Hydrogen molecule for both van der Waals radius as well as what? Covalent radius. First of all, I'm telling you, I'm warning you, you have no business to actually calculate van der Waals radius for hydrogen. You need not. You need not, because hydrogen does participate in what? Covalent bonding, and I think it will be prudent on your part of you that you just stick on to what? Covalent radius. Because why do you want to stick on? Because already we are running error and we want to minimize the error. And if that is the case, then the atoms must be close to one another. And for closing down, the force between the atoms must be of higher magnitude. And common sense says that the van der Waals force is actually very less weaker compared to what? Covalent force. You must understand. A van der Waals force is much weaker compared to what? A covalent force. Then if such is the case, then the adjacent atoms must be far away. They are far away. And we are looking at a situation where they are actually closer, right? So then what happens if the van der Waals force is weak? If it is weaker than covalent force, the adjacent atoms are far away, and then at that point of time, you measuring the van der Waals radius, then obviously the consequence would be the van der Waals radius is in fact greater than covalent radius. For hydrogen, you must understand this. When van der Waals radius is greater than what? It's almost like 30% greater, in fact, approximately. Van der Waals radius is almost 30% greater than what? Covalent radius. In such a cases, I think it's prudent for you to stick to what? Covalent radius for hydrogen, and don't get into what? The van der Waals radius for hydrogen. Then why is the van der Waals radius proposed in the first place? It is for inert gases and not for hydrogens and the other molecules which actually participate in what? Covalent bonding. So you stay away just for our theoretical importance to know how much percentage is van der Waals radius greater than what? Covalent radius. That's the reason why we are doing it. But otherwise, you must be staying away from doing it. Now, if that is the case, it will be at the best case proposition for actually what you do is the van der Waals radius is basically proposed for inert gases. In case of inert gases, you know, the issue with inert gases is they don't participate in bonding under normal conditions. They do participate. We have compounds of what? Inert gases. The labeling of inert is something now is obsolete, because even inert gases are participating in bonding. So what I do is they don't do it under normal circumstances, but I think they will be doing it at drastic conditions. But if that is the case, I think van der Waals radius it's best suited for inert gases. Now, if that is the case, if this is an inert gas molecule, inert gas atom, right? Because it's like helium, because they don't participate in bonding. The question of molecule doesn't arise. You cannot have He2. You cannot have argon diatomic molecule, or you cannot have the other radon diatomic molecules, because under normal conditions they don't participate in bonding. So all these are monoatomic. You must understand this, right? So if I take an inert gas atom here is the nucleus, and the positive charge, this is the positive charge, is actually in equilibrium with the negative charges. Right, the positive charge is in equilibrium with the negative charge, and then thereby this atom seems to be neutral. This atom is basically neutral. You know, there are two conditions for an atom to be neutral. If someone is asking you a question, when is an atom neutral, then you would be answering it, the number of positives equal to what? Number of negatives. But that's a wrong way of answering. That's an essential condition. But that won't be a sufficient condition for you. You must always say that the positive charge is in equilibrium with what? The negative charge. Then I think the atom will be neutral. In such a case, then you imagine another inert gas molecule where the positive charge is basically in equilibrium with the negative charge. Right, the same inert gas atoms, not molecules, please. I withdraw the statement of calling it molecules, but I think it's inert gas atoms, right? If I imagine another inert gas atom here, then when they are very close, then when I apply pressure, what you do is apply pressure, and in fact lower the temperature, right? This might, when I say apply pressure, and lower the temperature, these are not normal conditions. These are drastic conditions which are required. Then when you do this, the atoms are actually becoming close. They are actually becoming close now. When they close, this equilibrium, the so-called equilibrium, which is a sufficient condition for atom to be neutral, the equilibrium gets disturbed. And the disturbance of equilibrium, if I can draw pictorially, then somewhat it looks like this. It basically looks like this. Watch here. That's, the entire negative charge towards one side and the positive charge towards one side. You can actually say when the one charge is towards one side, the other charge will be naturally in the opposite side. I need not tell that. Then what happens is this positive might attract the negative in the other one because now they are actually close. And this is how they alternate positive charge and the negative charge. And now positive and negative, you will have a van der Waals force. Now you have a van der Waals force between them. But this van der Waals force doesn't exist under normal conditions. Remember that applying pressure and lowering the temperature, I think the molecules, the atoms are very close to each other, the inert gas atoms, and the equilibrium gets disturbed. Equilibrium disturbances, you have poles appearing. These are induced poles. They are not natural poles that are present in an atom. They are induced. They are basically induced, and I call this to be induced and justify it for the simple reason you have what? You are doing this at a drastic conditions. Now, if this is the case, then you can actually see this is the van der Waals force. When the van der Waals force existing, then he is telling that you take the internuclear distance between these two and then make it half, and this part is called the van der Waals radius, you must understand. So this is the fit case. This basically is a fit case for inert gases. Don't apply this for hydrogen atoms, chlorine atoms, fluorine atoms, where they are actually participating in what? Covalent bonding. If you apply, it will be stupid and it is foolish also. For the simple reason, because van der Waals radius involves van der Waals force, and the van der Waals force is weaker than what? A covalent force. So when we wanted atoms or molecules to be closer to one another as much as possible, or because already we are running error. So if you're taking the case where the atoms are far away, then I think it would be a different thing you must understand. So that's how the van der Waals force is, and this is more applicable, suitable for what? Inert gases. And I can claim that the van der Waals radius is almost 30% greater than what? Your covalent radius. That is how, that is of the theoretical importance, not for application, for atoms that participate in what? Covalent bonding, you must understand. That is the second part. Now coming to the third radius, then I think I go for ions where ionic radii. This is for ionic radii. Now look into the third category, that is ionic radii. Now why ionic radii? Because we have force, because as I said, the basis for giving 4 operational definitions is nature of what? Bonding, and one of the bondings is electrostatic force. That's what we call it to be an ionic force, and this is applicable only for ionic people who are participating in ionic bonding. So if that is the case, ionic radii. Now if I take NaCl solid, this is basically an ionic solid, and I call this to be ionic solid because this NaCl, it will be having ions. It will be having ions, not atoms. You must understand. NaCl is basically containing what? Ions. Now if you look into this is how, and you can see here Na plus and the Cl minus, and it will be containing Na plus and what? The Cl minus. That's how the setup is for the NaCl crystal, you must understand. There are no atoms of sodium, there are no atoms of chlorine, neither do you have molecules of NaCl. NaCl, the basic particles or the basic things that are available in sodium chloride is basically ions. So in such cases, then what happens if you have ions and these two ions are bound by ionic force? An ionic force itself is called what? An ionic bond. You must understand, a force is a bond. A bond is a force rather. So for all the ionic solids, you must be applying ionic radii. And if I can define this for you, then I think ionic radii is defined to be, its distance from the nucleus. It is distance from the nucleus. Its distance from the nucleus to that point. Right? Distance from the nucleus to that point. Which point? To which point? To that point where where the nuclear force of attraction ceases to exist. You must understand, distance from the nucleus. It's not half like your covalent radii or van der Waals radius, but it is ionic radii is the distance from the nucleus to that point where the nuclear force of attraction ceases to exist. For example, if this is the nucleus, you go to this point beyond which the nuclear force of attraction ceases to exist. So you have the influence still here, and this is what is called ionic radii. You must understand that is how ionic radii is defined, that to that point beyond which the nuclear force of attraction is ceasing to exist. That is how ionic radii is defined, and ionic radii is useful for species which actually form the fundamental particles in an ionic crystal, and the ionic crystal or ionic substance is made up of ions, and it's not made up of atoms nor what molecules. It's basically made up of ions, and since you have ions, you have an ionic force, and hence I call this to be an ionic bond, and this is how the definition is: distance from the nucleus to that point where the nuclear force of attraction ceases to exist. So that's how is ionic radii defined, and this is applicable for ionic solids. You must understand this, right? So we have basically done with the first one is covalent radii, second one is van der Waals radius, third is what? Ionic radius, and I have the last one, that is metallic radius. And if you're done with this, and here comes the metallic radius, you must understand, right? What is metallic radius? Metallic radius, right? Metallic radius, this is for basically for metals. Now what is so special in metals? Now very strange, this is the best thing what we can have, rather metallic radius, because earlier we wanted the atoms to be as close as possible. Remember, in covalent bonding, when the atoms are approaching for bonding, after some time they will stop at a distance. That distance is called bond length. So that the atoms, even though are approaching one another out of their own interest, they don't overlap with one another, right? They stop at a point. And that stopping at the point, that measurement is called what? Bond length. At that point, the potential energy basically increases, right? Similarly, in van der Waals radius, you have an error, huge error. We have to get into a drastic condition. In spite of that, the van der Waals forces are weaker, right? So in none of the cases, right, we will find that the atoms are supposed to touch each other. But in metallic radii, we have the privilege where the metals are solids, and the metals are solids, then the atoms are supposed to touch each other with 0 degree of freedom. Well, it's so easy for us, rather we need not struggle for it. So the atoms are supposed to touch each other. For example, if you take an iron solid, the iron atoms are basically touching one another in their setup. So I need not struggle for atoms to be touching one another, right? So the error is basically almost what? 0 in case of what? Metallic bonding, you must understand. So, right, if I take a metal and look into the metal atoms here, the metal atoms touching each other. Like if you look into the setup of the metallic solid, and if I say this is the metal atom, and the other metal atom is basically touching each other. It's touching one another. We are not struggling. We are not trying to get what covalent force or a van der Waals force by putting some conditions. Like this is the best case scenario where the metal atoms are supposed to touch each other, and that's what we wanted to reduce the error, right? If that is the case, then when the metal atoms are supposed to touch each other like this, right, in the metallic solids, then you take the internuclear distance between these two and then just make it half. This is metallic radius. We need not struggle the internuclear distance between the metals and then make it half. That becomes what? A metallic radius. It's not the case of covalent bonding where the atoms are approaching one another and we are waiting for the covalent force to exist between them. When they are approaching one another, they stop at a distance because that's when the potential energy is increasing. When they stop at a distance, that's what we call bond length, but they're not touching each other. So in none of the cases they touch each other, it is the metal atoms, except in metallic radii, you can actually see the metals are supposed to touch each other. When they are touching each other, then the internuclear distance between them and make it half is called metallic radii. So if I can define what is metallic radii, then I can simply say metallic radius is basically internuclear distance between atoms in a metal where they are basically supposed to touch each other. To touch each other. That's what is called what? A metallic radii. Without any problem, we have done it because they are already naturally, they are solids, and the solids, the atoms are supposed to touch each other. That's how it is. So if I can put everything in one frame for you before I go to the trend, what we are doing is we are basically trying to get into periodic properties in periodic classification. Periodic properties in periodic classification. Now what is a periodic property? A property that repeats itself its regular intervals in a period. Right? That's called a periodic property, you must understand. And in the process, the most fundamental thing where the entire chemistry revolves is atomic size or atomic radii. All right? We are discussing that. And we had an issues while determining atomic radii according to the ideal definition. So we are just hanging on the ideal definition for no use, and then we shifted toward the operational definitions in that regard, and I proposed 4 of them. And now what I'll do is I'll put all the 4 in one frame for you. Just observe carefully here. Just observe carefully. Right, I just beautifully describe all the 4 at one place. At one place. Let us actually see everything in one frame. Right, in one frame. So what we are discussing is the periodic property, and periodic property 1, that is atomic radii. Atomic radii. Now the issue is in atomic radius, first here is an atom, nucleus, and he wants this distance. This is called atomic radius, right? That is atomic radius. But this is difficult for the simple reason, right? Its position impossible to find. Impossible to find the electrons, right? That's Heisenberg's uncertainty principle. And then, first of all, even isolating one atom, not possible, right? When it's not possible, we have shifted our discussion to taking 2 atoms. So what I've done, I have alternate operational definitions proposed. Right, because this one is, the entire setup seems to be absolutely ideal. Absolutely ideal. So alternate operational definitions, and when I do this with errors, you can't eradicate the error. Then I propose all this, and the first one is the covalent radius, and if you actually see, this is what is the covalent radius. Right, this and half, this is covalent radius. This entire thing is bond length. So basically bond length is twice of what? Covalent radius. This is applicable for only people who participate in what? Covalent bonding. And if you look into the van der Waals radius, this is basically for inert gases. Inert gases, this is right the positive, and this is what is the positive of another atom, and basically this is most applicable for what? Inert gas atoms, right? Inert gas atoms. Then you have a van der Waals force between them. This is must, right? And then take the internuclear distance and then make it half. This is what? Van der Waals radius. And remember, these are not normal atoms. These are inert gas atoms. Mind you this, right? It's not useful when you apply van der Waals radius for hydrogen atoms, I was telling you. And then going for ionic radius, This is basically for ionic solids, right? Ionic solids, then you start from the nucleus, right, and go to the point, right, where from here onwards, after this point, nuclear force of attraction ceases to exist. And this distance is what? Ionic radius. And the most easy for us is basically metallic radius. If this is metallic radius, and this is for metals, and you can actually see the metallic setup. They are solids. So this is a metal atom. This is a metal atom touching each other. There you can actually see they are touching each other. When they touch each other, take this internuclear distance, and this is metallic radius, and this is a metal atom, and this is a metal atom, and you can actually see they are touching each other and the metallic radius. I put everything in one frame for you for an easy understanding. You must understand. Now, once we know what is atomic radii, let us check out what are the questions that will be asked in the exam and the trends which they exhibit while in a period or in a group in the periodic table. Now, what we'll do, now we have a complete idea of what is atomic radii now. Now what we will do is, how is this atomic radii varying in the periodic table? That comes to second issue now. This I can call, this, when I discuss all this, I will be basically linking this trend to questions in exam also, so I draw the attention of everyone now, right? Now first of all, what is the trend of atomic radii in the periodic table? Now first of all, let us take the case of in periods. Right, in periods, what is the trend and why? Right, that is how we will get into the explanation of that. In periods, what is the trend first? Look at the trend. In periods, the trend is atomic radius decreases from left to right. It basically decreases from left to right. You must be giving a reason for that. Now look into a second, you take a second period and explain this. If you look into the second period, I think it's lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. You must understand. Right, that is the second period elements. And if you look into the atomic number, then I think it will be 3 and it's 4 and this is 5 and this is 6, this is 7, this is 8 and 9. You must understand. Right, it's 3, 4, 5, 6, 7, 8, and this is nothing but atomic number. You must understand this. This is atomic number. That's nothing but the number of protons. You must understand the proton, the atomic number of protons in those particular atoms. And when I move from left to right, if you look into these configurations, well, if I can put the configuration of lithium for you, then it is 1s2, 2s1. Mind you, this is the outermost shell. You must understand. That's 1s2, 2s1. And if you actually get into beryllium, then it is 1s2, it's 2s2, mind you. And here 3 has become 4. This is 3 and this is 4. Right? What is happening here? Observe it from the beginning itself to understand. Right? The nucleus has grown by 1 unit. I draw the attention here, people who are listening. Why the atomic radius decreases from left to right, here is an explanation. It's a common sense. The issue is, from lithium to beryllium, the nucleus has swelled. The nucleus has swelled by 1 unit. Right? Nucleus has swelled in the sense the positive charge is increased from the nucleus. Right? When the positive charge is increasing, then the nuclear force of attraction would also be higher on the outermost shell. You must understand. So, if I continue, this is 1 unit increase from 3 to 4, but the electron we have started to be adding to the second shell. This is the shell number. That is the shell number. And now the nucleus has swelled, but the electron is added to the same second shell. It's added to the same second shell. Understand here. From here to here, the nucleus's size is increasing. The nuclear force of attraction has increased, but the electron is being added to the same shell, that is outermost shell. That's number 2. Number 2. You must understand. I'd like to explain again. This nucleus is swelled by 1 unit from 3 to 4 when you are moving from left to right. Nucleus has swelled means the number of protons have increased, the nuclear size has increased. So naturally the nuclear force of attraction would increase, right? One step in a period, the nucleus is swelling, the force of attraction is increasing, but the electron is added to the same shell. You can actually see the shell number. Shell is nothing but the number. That's nothing but the principal quantum number. You must understand. It is added to the same shell, second. Now if I go to the third one, if it is boron, which is 5, it is further swelled. The nuclear size is increasing. It is further increasing. But the electron again adds to the same shell, 2s2, 2p1. But remember, the shell number remains to be 2. The shell number remains to be 2. That means the electron is added to the same shell. What I'm doing is I started off with this much nucleus, then it swelled this much, then it swelled further, but the electron, the outermost electron, is added to the same shell, to the same shell, to the same shell. You must understand, right? So if I take one step like this, period, the nucleus is swelled, the force of attraction is increased, so the outermost shell is actually pulled inwards. Pulled inwards. Because you're adding to the same shell, that's number 2, right? If I take one more stride, then I think I'm pulling it further because the electron is added to the same shell. So what I can show you a pictorial representation. You started off with this nucleus and the size is increasing for the nucleus, but the outermost shell is this, right? That is the second shell. You have only one electron initially. Right, the swell is increasing, the size of the nucleus is increasing, the nucleus size is increasing, the nucleus size is increasing, the nucleus size is increasing, but the electron is added to the same shell, electron is added to the same shell, the size is increasing, the size is increasing, the size is increasing, the size is increasing, but the electron is added to the same shell, the electron is added to the same shell, same shell, same shell. So whenever there is an increase, the force of attraction is towards this side and the outermost shell is basically pulled inwards, pulled inwards, pulled inwards, pulled inwards, right? Whenever you're taking one step in a period, the size of the nucleus increases, but the electron is added to the same shell, thereby the outermost shell is basically pulled inwards, thereby the size is basically decreasing from left to right. You must understand, that is a trend. Right, left to right in a period, the atomic radius decreases. That's what is a trend. So how do you explain, basically, how do you explain this? Why it decreases from left to right? Then I think you can give this explanation in this fashion. Watch. From left to right, nucleus increases by 1 unit. You can actually see 3, 4, 5, 6, 7, 8, 9. It's increasing by 1 unit. But electron added to same shell. Same shell. So then what is happening? So the same shell, so the outer shell pulled inwards. It's basically pulled what? Inwards. Thereby the size decreases. You must understand. Simply speaking, I gave a pictorial representation. Whenever you go, it is increasing by 1 unit, but the electron is added to the same shell. Thereby the nuclear force of attraction is dragging the outermost shell towards itself. Thereby the size decreases from left to right. Well, one thing, if students are observing me very carefully, I'm very conscious. I'm basically conscious, and I think you might be asking a question to me. If you actually see, it is lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. Watch carefully here, right? And from lithium to fluorine, I have written and I've stopped it. I didn't write neon, right? This is the first group, this is the second group, this is the third group, this is the fourth group, this is the fifth group, this is the sixth group, this is the seventh group. But I did not touch the 8th group elements very consciously. Don't forget, don't think that I forgot writing for you. No, absolutely, I didn't forget. I'm very much conscious of what I'm doing here. Right, very consciously I stopped at the 17th group or the 7th group. You must understand this. I just don't want it to write the 8th group. And if you ask me why, that's a question which is in fact asked in exam. In fact, that is a question which has been asked in exam. That's a question which is asked in exam. Why? Now here, Now, I would like to pose that question to you because that's a question which is important for your JEE. Which of the following is correct? Which of the following is correct? That's one thing which people will ask you, right? And remember, but before I go there, I just wanted to tell you, how do you explain the atomic radii trend in the periodic table? I think in the period, the atomic radii decreases from left to right. It decreases from left to right. The best explanation is from left to right, the nucleus increases by nucleus size, or a nuclear atomic number increases by 1 unit. It increases by what? 1 unit. But the electron is added to the same shell. Then the nuclear force of attraction is so high at each and every stride, the outermost shell is pulled inwards. Thereby the size decreases. But if you notice, I have stopped here till 7th group itself. I didn't go for the 8th group. There is a question for me. Why didn't you do that? Well, if that is the case, let's put the question to you. Let's write down the answer. Now, noticeable thing here is basically, I would like to highlight this. So, even though I write this question to you, even though atomic radius decreases from left to right, even though atomic radii decreases from what? Left to right, we notice a jump between the 7th and the 8th groups. You must understand. 7th and the 8th group. 7th is halogens, or in the modern periodic table, we call it to be the 17th group and the 18th group. Right? From left to right, the size is decreasing, and I was giving an explanation to you. But the noticeable thing is, between the 17th group and the 18th group, you actually see, you find a jump between the 17th and the 18th. And what is the reason for that is the question. And this is the question in JEE or the BitSat or whatever you're writing. That question must be answered. You must be having that knowledge of why such a thing would be happening. Right? So what I mean to say, first understand the question. I pose the question to you. The question is, even though atomic radius decreases from left to right in a period, left to right the size decreases. But what happens, this decrease is noticeable only till the 17th group, and between 17th to 18th, you find a jump in atomic radii, right? There is an increase in atomic radii. Why such a thing would happen and what's the reason for that? Let's actually understand this. What is the reason? Well, if you look into the second period, that is lithium, beryllium, boron, carbon, nitrogen, and oxygen. And if you look into the size or atomic radii, lithium is smaller compared to, lithium is greater than beryllium, is greater than boron, greater than carbon, greater than what? Nitrogen, greater than what? Fluorine, you must understand. Oxygen greater than fluorine. So you can actually see lithium is the biggest atom in the second period, you must understand here. It is in the second period, lithium is seen to be the biggest because the biggest atoms are placed to the extreme left in the periodic table, and lithium belongs to alkali metal, so it should be the biggest among that period, right? So this is fine. This we have understood till the 17th group. This is the 17th group or the 7th group we say. But what happens after the 7th and the 8th, right, that is neon here, you find a jump. You find a jump in atomic radii between 7th and 8th. What is the reason is a question which is asked in exam. Till 17th, you had a decrease. Between 7th and 8th, you had a jump. What is the reason? Which of the following is true is a question which is asked in exam in your JEE. Right? If that is the case, then you have to answer like this. Till the 7th, we consider, watch carefully. I draw the attention of everyone, please. I draw the attention of everyone. We consider, right, covalent radii till the 7th. Till the 7th. Because these are all the first elements of that particular groups. And the first element of every group will be participating in covalent bonding. You must understand. You must understand. So till the 7th group or the 17th group, we consider covalent radii, right? And for eighth, we are forced. It's no one's choice. You're no one's choice. You don't have a choice. You don't have a choice. You don't have a choice. We are basically forced. We are forced to consider. We are forced to consider van der Waals radius. We are forced to consider van der Waals van der Waals radius in case of what? Inert gases. That is what our discussion was. You must understand. That's what our discussion was. So till 17th group, you're fine going in for covalent radii. But for the inert gases, we are actually forced to consider what? Van der Waals radius without any choice. After all, inert gases do not participate in any type of what? Bonding. And we all know van der Waals radius is greater than covalent radius. And almost I was telling you that van der Waals radius is 30% greater than what? Your covalent radius. So naturally, till the 17th group, we are considering covalent radius, whereas for the 8th group, where the inert gases are, they don't participate in bonding, and thereby, we are considering van der Waals radius for them. You must understand that, right? So what is the question? The question is, even though atomic radius decreases from left to right, we notice a jump between the 7th and the 8th. What is the reason? And I told you we are forced to consider what? Van der Waals radius in case of what? All the 8th group are inert gases, and van der Waals radius is almost 30% more than what? Covalent radii. So naturally you will look into a jump. You cannot ask me a question that why did you consider van der Waals radius for inert gases? It's no choice of mine. It is must to consider van der Waals radius. You don't have any option. So I write these wordings that we are forced to continue with what? Van der Waals radius. You must understand this, right? Now what we'll do, we'll discuss atomic radii trend in a group. Earlier I was discussing in a period. In a period you can see that left to right the size decreases, and I was telling a case where even though it decreases from left to right, there is a jump between the 17th group and the 18th group. Now let's see how the trend of atomic radii in a group. The trend, let me write it first, right? It increases from top to bottom in a group. It increases from top to bottom in a group. You must understand. Now if you ask me why there should be an increase, let us take the case of the first group. Let us take the first group elements. Now if you look into the first group elements, it's lithium, it is sodium, it is potassium, it is rubidium, it is cesium, and now you have francium. That is the first group elements. In the first group elements, what is happening here? Here the atomic number is 3, right? It is 11 and it is 19. Come on, it's a huge jump. It's basically a huge jump from 3 to what? 3 to what? 11. And from 11 to 19, the nuclear size is increasing, so many fold. Not the case where a period where it is increasing by one unit. Monotonically it is increasing, right? But in a case of a group, the nuclear size is growing. This was this much. Now this has grown this much, and this has grown this much, and further it grows down the group. But what did I write? The size increases from top to bottom. Well, if I can write the configuration, this is the nuclear size which is growing. But look at the configuration. It is 1s2, 2s1. And I'm underlining the outermost shell. This is the outermost shell. That is the second shell. So you can say electron added to the second shell. Right? It is electron added to the second shell. Now, if you go to the sodium configuration, it's 1s2, 2s2, and it is 2p6 and 3s1. Come on, man, it is third shell now. It is a third shell now. And electron added to third shell, and it is a new shell. You must understand that. So even though there is an increase in size of nucleus from 3 to 11. It's almost like 8 units increase, but the electron is not added to the same shell. It is added to a different shell. You must understand. Different shell. Now, what is the consequence of doing that? Now, what happens is, between the nucleus and the outermost shell, if you actually see, between the nucleus and the outermost shell, that's number 2, the number of shells in between them is only 1. You have the first shell in between the nucleus and the second shell. Now, in the second case, between the nucleus and the third shell, you have shell number 2 and shell number 1. So the number of shells are also increasing. The number of shells are also increasing. And I was telling you always, I was reminding you always that electron itself is a shell. So when I say number of shells are increasing, I can say even number of electrons are also what? Increasing. You must understand. So between this, look at the language what I'm using. Look at the language what I'm using. In a group from top to bottom, even though the nuclear size is increasing, the electron is added to the second new shell, always to the new shell. Now, if you look into this configuration, it's 1s2, 2s2, 2p6, 3s2, 3p6, and it is 4s1. Come on, this is electron added to fourth shell. Fourth shell, and this is new, right? So down the group, even though the nuclear size is basically increasing, the electron is added to a new shell. So when a new shell is coming into the existence, what is the consequence of it? So how do we actually view and explain this is, you have to say like this, between the nucleus and the outermost shell, you have one more shell in between, that is the first shell. First shell, having what? 2 electrons, you must understand. Similarly, in case of sodium, between nucleus and the outermost shell, that is shell number 3, you have 2 more shells, shells. I'm speaking of shells. I'm asking you to remember the number. It's all about number, not the subshells. Number means the designated number is the principal quantum number which I'm referring to. So between this nucleus and the outermost shell, this is the second shell, and this is the first shell. You must understand. So between this nucleus and the third shell, you have 2 more shells in between them. 2 more shells in between them. You must understand this. 2 more shells. And when you have 2 more shells, they will be having electrons. They will be having electrons. Similarly, in case of potassium, where the number of units have again gone 8 units more. 8 units more between the nucleus. We have to explain like this. If someone is asking you, please explain like this. Between the nucleus and the outermost shell, between the nucleus and the outermost shell, look into the number of shells now. This is the third shell. This is the second shell. And this is the first shell. So look into, from the beginning, between the nucleus and the second shell, you have 1 shell more extra. In case of sodium, between the nucleus and the third shell, you have 2 more shells, second shell and the first shell. And in the case of potassium, between nucleus and the outermost shell, you have 3 shells, that is the third shell, second shell, and the first shell. And the first shell. So, what is happening, even though, I quote like this, even though on moving from top to bottom, the nucleus is swelling, swelling with positive charge, the electron is always added to a new shell, a new shell is added. That's not the case in case of periods where the electrons are added to the same shell. So the force of attraction was increasing and the outermost shell is pulled inwards. Whereas in this case, I think the size increase of the nucleus is basically compensated. I'll use the word, is compensated. It's basically compensated, right? By addition of a new shell. Thereby what happens is the effect of the increase of this nuclear force of attraction is basically not falling on the outermost shell as it would have been if it would have added to the same shell. Since the addition of new shell comes with new electrons, I think they are basically neutralizing and not allowing this increase of nuclear force of attraction to fall on the outermost shell. If you don't have the nuclear force of attraction falling on the outermost shell, then the outermost shell will relax. An electron being a wave, it will be relaxing, means it will be relaxing away from the nucleus, and thereby the size goes on what? Increasing. You must understand this, right? So how do you describe this? I would like to write it here. Watch carefully. I'm writing here why atomic size or atomic radii increases in a group. Then I would like to say, right, from top to bottom, nucleus size increases. Nucleus size is what? Increasing. There is no doubt in that. But electron added to a new shell. So whenever you're going down the group, one element down the group, the nuclear size is increasing. You can actually see here it's increasing. But at the same time, this electron is added to a newer shell. So added to a new shell, and I would like to say this addition of new shell actually shields the increased nuclear force of attraction. This addition of a new shell and the number of shells being increased between the nucleus and the outermost shell, well, you understand, then the consequence is the size increases. You must understand here. So how do you explain in a beautiful way? Understand that from top to bottom, the nuclear size increases. There is no doubt in that. But the electron is added to a newer shell, and this addition of new shell, this addition of new shell is compensating the increased nuclear force of attraction. So the outermost shell is not bearing the increased force of nuclear attraction. So thereby the outermost shell is basically relaxing. It's basically relaxing, and then what happens is down the group, one stride down the group, I think the atomic radii is also what? Increasing, because it's been compensated. You must understand this, right? So what is the trend? The trends are simple. One, what is the trend we are discussing about? Atomic radii. Well, it decreases from left to right, and atomic radii, this is in a period. And in a group, size increases from top to bottom. You must understand this, right? That's about atomic radii, and then we'll get into another periodic property, and this is atomic radius, and we'll get into another periodic property and check it out. There's some questions we would like to link it up with your exam also. So the first periodic table is it's basically all about atomic radii. I told you in detail. If you have missed out on something, you just rewind it, relax, sit relaxed. I think it's almost like you are in a classroom, relax, and then get through each and every point. I think you will be feeling confident, and you will be writing your aptitude exam. After all, the exams, the pre-engineering tests, what you're writing are absolutely aptitudes, and writing aptitude exams requires understanding of the subject. You can check my lectures anytime you want it, right? We'll take up the other periodic property in the next class.